Inside this booth is a motion picture camera which is taking pictures through this window. We use a soundproof booth. When it's closed, it keeps the camera noise away from the microphone. The camera is operated by a motor which runs at exactly the same speed as the motor in the sound machine. Whew, it's hot in this booth. Let's get out on the set again, and I'll show how the sound is picked up by the microphones on the stage. Sound waves are picked up by this wonderful mechanical ear, the microphone, which is really a glorified telephone transmitter. This microphone changes the sound waves into electrical vibrations, which are amplified here and sent along these wires to the mixer room. The sounds from the stage microphones are mixed here so that it's natural for the action in the production. Mr. Mixer sees the actors through this window and hears them only through this horn. Now that we've got the sound right, I'll show you how it's amplified. Get ready. The power from the microphones is amplified about 10 million times by these vacuum tubes, making the voice current strong enough to operate the machine that photographs the sound. Do you follow me? This is the machine that is used to record the sound on film. This sound film is traveling at the same rate of speed as the picture film in the camera booth. The light valve has two thin metal strings stretched across this tiny slit. On one side of the slit is a strong light, while on the other is a film, moving at exactly the same speed as the picture camera in the studio. The greatly amplified voice currents passing through these tiny light valve strings move them closer together or further apart, thus changing the size of the slit. Therefore, the light varies as it passes through this rapidly changing opening, leaving a true photographic record of the voice currents on the film. Simple, isn't it? Huh? Now let's look at the films after they've been developed. Well, here we are. Here are our two negatives developed. The next step is to print these two negatives onto a third piece of film. We'll print the sound record first, and then the picture record. Here we have a completed sound print, and we are now ready for projection. This is the picture and sound projector. One motor drives both the picture and sound equipment. You see? Let me illustrate this with a simple diagram. This lamp illuminates the soundtrack on the film. The light from the lamp passes through the slit, throwing a very narrow line of brilliant light on the soundtrack. As the film runs past this light, the marks on the soundtrack cause the light to increase and decrease. This light, in turn, causes the current through the photoelectric cell to increase and decrease, thus reproducing the electric vibrations first created by the sound waves. The current from the photoelectric cell is pepped up by the amplifier, and then this amplified current is carried by wires along through the theater and down to the screen on the stage to connect with the loudspeakers. This is a typical layout of the stage set with two horns behind the screen. The receivers connected to the horns convert the electrical vibrations back into sound waves exactly the way the telephone receiver operates, so that while the picture is being shown, the sound which was recorded is reproduced in step with the picture. The screen is full of small holes so that the horns may be placed behind the screen to let the sound through. This gives the illusion that the sound is coming from the image of the speaker. Talkie, there goes your cue. You're next on screen, while Muty can go try on his new voice.
Okay. Just a song at twilight. When
Whoopee! I found my voice! Ha 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 ha!
The biggest catch in making road maps is keeping them up to date. Modern map makers have solved this by developing a trick method of printing. Revised maps can be put out every 2 weeks. By this method, maps can have their faces lifted without fuss or feathers. Here's how it's done. Every time a road is to be built or repaired, symbols showing its progress are overprinted onto the latest edition of the regular road map. The map company's expert draftsmen spend all their time checking road reports and drawing in symbols indicating latest road conditions. These symbols are first drawn on transparent sheets laid over the original master map, from which all road maps of that district are made. This particular symbol, for instance, shows that certain roads are under construction but that detours are provided. This symbol will be drawn over every road that fits this classification at the time the map goes to press. But wait a minute. How does the draftsman know all this? It's a cinch he can't walk every mile of every road in the United States. Well, somebody has to. Who is this fellow with the 7-league boots? This work is done by field men, road scouts who each year travel the equivalent of many round trips to the moon. As a rule, these map detectives work in pairs. One man driving the car as the other plots road changes on his special chart book. Notations are carefully checked against special instruments to ensure complete accuracy. Drawing a straight line in a moving automobile on a bumpy road is one job that calls for a steady hand and a car that smoothly cooperates. These road changes, when carefully drawn to scale in the graph books, are now ready for the big leagues, the master detour maps in the drafting rooms. Here is another type of symbol often found on up-to-date detour maps. This one indicates road under construction, but open to traffic. In other words, drive with care. Automobile club scouts like these also run down valuable road clues. These men often do 2 jobs at once. Besides gathering data for the latest detour maps, they also check new findings against old United States Geological Survey topographical sheets. On these, they not only indicate the topography of the land, drawing in all mountains, canyons, and rivers, but they also check official mileage figures from point to point, comparing them with those already listed on the survey sheets. Since many of these were drawn up from surveys made over 30 years ago, some roads are found to be longer or shorter than their birth certificate shows.
John Mockley, a physicist, and a talented 23-year-old engineer, J. Presper Eckert, wanted to build an electronic computer. Their design was awesome, proposing to use some 18,000 vacuum tubes to do the lightning-fast arithmetic. The experts were scornful. It was a well-known fact that vacuum tubes were unreliable. They tended to burn out. One authoritative estimate was that a machine with 18,000 tubes would break down about every 5 seconds. It filled a room 50 feet by 30 feet. As well as its 18,000 tubes, it had tens of thousands of electrical components and 500,000 soldered joints. They called their creation ENIAC, for Electronic Numerical Integrator and Computer, and it could perform 5,000 additions every second.
When the neighbors drop by for a slideshow, it's fun for everyone. But what's the answer when you want to run off both regular-size slides and oversized slides? The answer is the new Enscomatic, the A-plus slide projector from Ensco. It's the world's only fully automatic projector to take all popular slides: cardboard, glass, metal, and plastic. And when it's time for those big 2 1/4 slides, no problem, Enscomatic projects them clear and sharp. And Enscomatic runs itself, or with the remote control, you can control your slides from anywhere in the room at any speed you choose. At the end of the show, Schematic even turns on the lights.
The turning point came in 1923 when Dr. Zworykin invented the iconoscope. This tube, after years of further development, became the image orthicon, the electronic eye of the modern television camera. In 1929, Dr. Zworykin and his associates announced the first successful electronic kinescope, forerunner of today's television picture tube. The circuit was complete. All electronic television was achieved. It worked. How? The lens of the television camera acts like the iris of the human eye. It gathers in the light rays and focuses them on a mosaic of light-sensitive material that is built into the picture tube. The light-sensitive material converts the light into electrical impulses, a reaction varying with the strength of the light. The optic nerve of the camera picture tube is the electron beam, controlled by electromagnets. The beam scans the picture which is on the plate in rapid sweeping motions from side to side, from top to bottom. When the beam hits the image, it loses varying amounts of electrons and then bounces back to the opposite end of the picture tube, where it is amplified millions of times. It is led off to the transmitter in the form of electric current. The signals are broadcast as radio impulses into space. Heart of the receiving set is the kinescope. Here, the action is reversed. The stream of electrons, synchronized perfectly with those of the camera tube, literally paints the picture information on a chemically treated screen line by line. The glow is bright when the beam is strong, less bright when it is weak. Thus, the picture is reassembled.
Let us now look at some actual PNP germanium transistors. They are sealed in glass covers like the diodes. This lead goes to the emitter, this one to the base, and this one to the collector. With the cover removed, you can see the construction. There is a central strip of N-type germanium, and on the left, fused into it, is a small blob forming the emitter, and on the right, a larger blob forming the collector. And here is a transistor connected as we saw in the diagram earlier. That's the emitter, the base, and the collector. The emitter is connected through this milliammeter and a resistance, not shown, to the positive pole of a battery. The base is connected through this milliammeter to the negative pole of the battery. The collector is connected through this milliammeter to the negative pole of another battery, and the positive of the battery goes to the base. The emitter current, 4 milliamps in this case, splits up into two parts. The collector current of about 3.8 milliamps and the base current of about 0.2 milliamps. Now watch what happens when we vary the base current. Notice that a small change in the base current produces a large change in the collector current. This is the way we obtain amplification. The transistor can be used instead of an ordinary valve in all kinds of electronic circuits with many advantages. For example, any apparatus employing transistors can be made lighter and more compact. Not only because the transistors themselves are smaller, but because they require such a small power supply. This portable valve radio needs this low-tension battery and this high-tension battery to operate it. In the transistor radio here, this small low-voltage battery is all that is required to operate the receiver for an equivalent time. Another advantage is illustrated in large equipment like this electronic computer. When using valves, 5,000 of them in this case, quite elaborate ventilation systems are required to remove the heat generated by the valves. In transistor-operated equipment, there is practically no heat generated, and the transistors may be mounted close together on panels like this alongside the other components. One of the earliest applications of transistors was in hearing aid apparatus. This hair grip contains one, complete with amplifier, battery, and microphone. Transistors have developed rapidly, from small ones like this to the larger power-type transistors. Research into new techniques continues, and fresh applications are being discovered all the time.
Take the remote unit from its handy storage space, and you're set for hours of pure pleasure. Enjoy your favorite programs, black and white or color. Turn the set on, select your channel, see all color shows in living color. Once you've adjusted fine-tuning for each channel, you never need touch fine-tuning again, either at the set or on the remote unit. But if you want, touch, and you can adjust fine-tuning to suit your taste at any time. If you overtune on this or any other control, just push the companion button to reverse the direction of the control. In the same way, press this rocker bar to adjust the color, variable all the way from black and white to maximum color intensity. To adjust the tint control for natural face tones, press the right rocker bar.
In 1890, Dr. Herman Hollerith developed the method of storing information on punched cards. By the turn of the century, early key punch machines enabled clerks to transfer numerical information from original documents to punched cards which a machine could read. Other cards were stored in tub files until the information on them was needed for updating or processing. Then all the cards would be sorted mechanically in this old vertical sorter. The resulting total is on this early tabulator and written down by the machine operator. Though this equipment was fast and accurate in its time, it was very limited in function. No subtraction, multiplication, division, or alphabetic characters. So the users were anxious for an improved data processing technology. Thus, new technologies were developed during the first half of this century to provide faster, more flexible accounting and record-keeping machines which were capable of performing information handling services for business. These machines, of course, were not computers. They were just fast, high-volume adding machines. In large organizations, these punched card systems required many machines, many operators, millions of punched cards, plus large amounts of floor space. Again, large users began asking for a new technology to process large volumes of transactions and to organize and present facts in a form they could use to better manage the business. Enter the computer and a new age. The Mark I, our first computer, was unveiled at Harvard University. It took another 10 years of development before the first production computer was installed at Monsanto in 1955. The first generation of computers that were installed from 1955 to 1960 were originally designed to do scientific and engineering jobs. Characteristically, they had slow information input and output performance, but their computing power was the marvel of the 1950s. Organizations with large volumes of commercial applications quickly adapted the scientific computers to do payrolls, invoices, and production control work. Once again, the users developed a need for a new technology. Why couldn't we have computers with fast information input and output for commercial applications? Fortunately, there were several major technological breakthroughs in the late 1950s. Transistors and printed circuits were developed, with their vastly improved speed and reliability over vacuum tubes and wires. A new automated process for manufacturing magnetic core memory devices made it possible for low-cost computer systems to efficiently sort thousands of records. Card input units, tape drives, and printers now could offer for the first time the speed and versatility needed by large commercial users. The combination of these advances brought about a second generation of computers in 1960 with the delivery of the 1401 system. This second computer generation, with its vast improvements in processing speed and capacity, made extensive use of tape input-output systems, especially for record-keeping jobs. Year-to-date records on tape could be read into or out of computers at the previously unheard-of rate of 41,000 characters per second. Besides speed of access, tape could store an enormous amount of information for its size in comparison with punched cards. A standard reel holds 2,400 feet of 1/2 inch wide tape and can contain data equivalent to about 400,000 fully punched cards, or 200 card boxes filled with punched cards.
The Sony Betamax. Its only purpose is to serve you. This totally new concept in home entertainment will expand your enjoyment of television viewing to a level that was, a short time ago, nothing more than an ambitious dream. With the Betamax at your command, you'll never again be deprived of watching whatever program you desire at your convenience. You'll be free of the restrictions of time. Its uses are defined only by the limits of your imagination. Since the Betamax has been equipped with an auxiliary tuner, you can record one program while you're actually watching another. Activate the Betamax videotape recorder. Insert a Betamax cassette. Press the forward and record buttons and you've done it. Schedule conflicts are now a thing of the past. You record what you want and play it back when you want. Finally, as the perfect complement to the Betamax videotape recorder, consider the Trinitron experience. The Sony Trinitron is unquestionably the most advanced achievement in color television viewing.
Marty, shh, you'll scare the fish.
But we're missing the big football game.
Relax, my VHS home video recorder is taping it right now.
Terrific.
Watch.
Terrific. But suppose it's over 3 hours.
Relax, Panasonic VHS tapes up to 4 hours of sports, movie specials on one cassette.
Wow. This VHS is for me. We caught the whole game.
Best catch of the day.
Yeah.
VHS, the 4-hour system from Panasonic and other leading companies.
There's nothing we want to watch on TV tonight, but we're still going to watch something great with our RCA video disc player and video discs. Just flip a switch, and on our TV, we see Airplane or The Pink Panther, The Godfather or Grease, Muppets, Monsters, Mickey, MASH, and 100 more, starting as low as $15, and the player costs less than $500. Put it this way, we're watching a great movie, and you're watching us.